temperatures end up working, right? So we know that we can find the work in a closed system if we have the pressure-volume relationship, because work is the integral of PdV. And then we started briefly last class talking about how we can find the change in internal energy, first by knowing the mass of the system, which in a closed system, remember that mass remains constant. And then if we can use tables to find the change in the specific internal energy, then the mass times the change in the specific internal energy will tell us the total change of the internal energy in the system as it undergoes a given process. Then, if we use the first law, if we know the work and we know the change in internal energy, then we can find the heat transfer. So that's kind of basically what we'll be doing between now and the first exam. Right now, the problem becomes is how do we find delta U, right? And there's lots of different strategies we'll talk about, but we've started to talk about this idea of linear interpolation, particularly with steam, right? So with water tables or steam tables, right? So yesterday, our last class, I think I introduced this idea of this TV diagram, a temperature versus volume diagram, or we can do the same thing with a PV or pressure versus volume diagram. In both cases, you have this thing we're calling the vapor dome in the middle, right? And it kind of segments where we expect different phases of a substance, like water, to exist on the diagram. So if we're above the vapor dome and to the left, right, so above this blue line here, then we expect, if we're talking about water, we expect this to be liquid water. And if we're using the textbook tables, right, or the copy of the textbook tables that's on my courses, then we would look in table A5, or I think it's A5E if you're using English or imperial units. If we're above the vapor dome and to the right, so above that red line there, then we have water vapor or steam, right? So this is, there's no more liquid left in this mixture. We're all steam and we're above the boiling temperature, right? And in that case, we would look in table A4. We're going to get some experience using these tables in this lecture. And then sometimes we'll be in this case, right? Maybe we're making macaroni and cheese, right? We're boiling water, so we have some mixture that's liquid water and vapor, right? So here we're going to use table A2 or table A3, depending on whether or not we know the temperature or the pressure. And hopefully you'll get a better idea of what all this stuff means as we go through some examples today. Right? So we have some regions here where it's single phase, right? If it's a single phase mixture, or I guess not a mixture, if it's a single phase, then what we have is a case where the temperature and the pressure are independent variables, right? Because remember, what we want to do is fix the state. If we find two independent intensive properties, then what we can do is we can fix the state, and that will let us find the specific internal energy. Right? So if we're above the vapor dome, then if we know the temperature and the pressure or any other two intensive properties, then we're good to go. Right? But under the vapor dome, that's not always the case. Maybe we need a different parameter, something like quality, which tells us kind of the mass fraction of vapor inside of our mixture. Right? So if we're in this single phase region, then what we're going to do is we're going to try to define this interpolation factor, A, right? So there's lots of different ways to do linear interpolation. Basically, what we're recognizing that all of these properties change non-linearly with whatever property we know, right? So let's say we know the temperature. But we're going to say that, well, let's pretend that our data points are close enough together that if I approximate the change between these 2 points as linear, I'll get an answer that's okay. Right? That's reasonable, right? Even though there's going to be some curve in between these two lines, if these lines are close enough together, our deviation from the actual answer will be small, right? And the nice thing about doing a linear interpolation like this, right, is we have this interpolation factor, and that's kind of like the percentage of the range that I went between these two known temperatures, right? So let's say I went 20% of the range in temperatures, that means I also have to go 20% of the range between the internal energies, or the specific internal energies that are associated with those temperatures. Right? I know talking about math like this sometimes gets a little bit confusing, so we'll do a couple examples today. All right, so we'll start here. I'll go down because I have, if you look at the other videos that are online, the examples are done sort of animated through PowerPoint. So I thought in this live lecture I would go through the examples on the tablet like this, and then you kind of have your choice of which video you want to watch. Right? So we'll start with this first one. Right? So it tells us that the pressure is 1 bar and that the temperature is 400 degrees. Now, this one, the first thing we want to do, right? We want to say, are we a subcooled liquid up here, right? Are we a superheated vapor, or are we a two-phase mixture? That's kind of the first thing I always want to do with these kind of problems, is figure out where I am on something like a TV diagram, right? Or if it's a PV diagram, I'm going to be in the same sort of region on the diagram, right? Now the nice thing is that 1 bar is approximately 1 atmosphere. Remember, 1 bar is 100 kilopascals, and typically atmospheric pressure we would say is 101.3 kilopascals. So this is approximately atmospheric pressure. Now, if I asked you what temperature water boiled at atmospheric pressure, you might know the answer in degrees Celsius, right? So here, if I draw a constant temperature line here, right, it would look like this. This would be, right? And I would have a constant pressure line of 1 atmosphere that would go like this, right? Remember, it goes up as we move left to right, and then it's flat under the vapor dome because temperature and pressure are dependent here. And then it goes up again once we get past the vapor dome, right? So this line is 1 atmosphere, or let's say 1 bar, because that's our answer here, right? So now here, if I look at 1 bar, maybe I know this already, or maybe I don't. If it was 1 atmosphere, this constant temperature line where water boils, that's where we're flat under the vapor dome. If it was 1 atmosphere, this would be 100 degrees Celsius, but we're a little bit less than 1 atmosphere because we're at 1 bar. So this is 99.6 degrees Celsius. But the temperature we want is 410 degrees, right? So that's up here somewhere, right? So that means that we intersect our line somewhere over here in the superheated vapor region, right? So now this was table, if I'm remembering right, I think this is table A3 and this is table A4, right? So as long as I got, it is this table, right? But I think this is table A4. So what I would do is I would come down and I'd look in the back of the textbook and I'd look for properties of superheated water vapor, right? I'm pretty sure this is table A4. Now, if I do that, I'll see that this table A4 is actually a bunch of different tables. It's a bunch of small tables, and these tables have in their heading have a pressure, right? So here I know my pressure is 1 bar, so that's good because I'm right here on this table, right? So this is the correct subtable for me. Oh, we got a question in the chat here. Oh, that's okay. So I will post a live video too, and then there's the pre-recorded videos as well. Right, okay, so we're at 1 bar, and then our temperature is 410 degrees. Now, the way these tables are laid out, these temperature rows are the same, right? So here, notice they don't have temperature in this table. It's because they go across. So this is all taken from the same page in the textbook. So here, we're somewhere between 400 and 440 degrees, right? So we're in between these two numbers. Right, so this is at 400, and this is 440. So I'm in between these two numbers, and what I want is I want to linearly interpolate between those two numbers. So I'm going to define my interpolation factor A. Now, I always define my interpolation factor by the property that I know, right? So here, I know the temperature, right? The pressure is good, right? That gave me the right table. I've used that information already. Now, I want to know something about the temperature. This is my range of temperatures between 400 and 440. So what I do is I take the actual temperature I'm looking for. This is 410. Now maybe you've already done this in your head, but it's good to systematically go through this, right? This would be, I guess maybe I'll write it out symbolically first. T minus T min divided by T max minus T min, right? That's 410 minus 400. T max is over here. This is 440 minus 400, right? So this is 1 divided by 4, or 10 divided by 40. That's 0.25, right? So if we were drawing our linear graph, right, where temperature, like so here, this would be 400. This would be 440 over here. And now here, we have the specific internal energy that goes with 440 is 2968-ish. 2968. Right? That gives us this point here. And this other point is 3032 or 3033-ish. 3033. Right? So we're saying we're going to assume that it's linear between these 2 points. Right? And we're at 410, which is 25% of the range here. So we go up here, and this is the actual point that we want. And then we go over here, right? So now we got to find out what that value is. You know, maybe if this was high school math or something, they'd tell you, you know, construct an equation, y equals mx plus b, and then you can find it that way. And you can certainly do it that way, but I think it takes longer than if you do this, right? So because this is linear, and we've gone 25% of the range between the temperatures, we also must have gone 25% of the range between these two values of u, right? So here, we know that A is also got to be equal to u of the temperature we're looking for minus u min divided by u max minus u min. Right? So now, if we look at this equation, when we did this equation up here, right, we knew these temperatures, and we were trying to find A. Right? Now we found A, we know u min and u max, and the thing we're trying to find is ut. Right? So now we're going to rearrange this equation, right, so that it's u at the temperature we're looking for is equal to, I'll move this u min over to the other side. So this is going to be u min plus A times u max minus u min. And in our case, that's going to be u min is 2967.9 plus 0.25, so a quarter of the range between these two numbers, which is 32.6 minus 2967.9. Right? And this is all, these are all in units of kilojoules per kilogram, except A, which has no units. I'll open this back up just to see what the number is, because I don't have my calculator here. You can work through this if you like, but the number that I got here, U of 410 at a pressure of 1 bar is equal to, I guess we could say is approximately equal to, because here we're assuming that it's linear between these 2 points, is 2984.1 kilojoules per kilogram. So does that make sense, that process? Does anybody have questions about that process? So this problem, it asks us, we won't do it, and some of the homework problems maybe ask us not just about specific internal energy. They might ask us about, the headers are cut off here, but this is specific volume on the left, specific internal energy. H, little h is enthalpy, and little s is specific entropy. And we can do this same process for any of them, right? So here I did the ones that are specific internal energy, that's these two numbers, but I could also find the specific volume is 25% of the range here, and specific enthalpy and specific entropy, I could find them all, right? The process is the same. Now, here this one could be a little bit tricky, right? Because when we look at this list, right, we know that temperature and pressure are not always dependent, or are not always independent. They're only independent if they're, so this one was a superheated vapor. So we could fix this state. That's good, right? These two we're also not sure. This one, anytime you have quality, you can fix that state. Pressure and quality, that's good. Temperature and quality, that's also good. Temperature and specific volume are also always independent. So I don't know if I can fix this state yet, but we'll try. Right, so now we have a pressure of 0.8 bar and a temperature of 220 degrees Celsius. This one ends up being the hardest one on the list, but I'll walk you through the process here. So the first thing here is, again, we want to, we'll draw our temperature versus specific volume graph, right? We've got our vapor dome in the middle. We don't know which part of this we're at. Right, now maybe you can guess because the pressure is less than atmospheric pressure, so maybe you can guess, but I don't really know, right? So if I don't know, I'm always going to check here first, right? So does it work under the vapor dome, right? So here, if I go under the vapor dome, this is my pressure in bars. So here, this is table A, I never remember if this is A2 or A3. Right? One of them has pressure on the left-hand side, and one of them has temperature on the left-hand side. Right? So this is basically saying, if my pressure was 0.8 bar, then my boiling temperature is 93.5 degrees Celsius. But my other graph is saying, well, if water is boiling at 60 degrees, then the pressure must be about 0.2 bar. Right? So this is telling you, if you have this, if you're under the vapor dome and you know the pressure, then you automatically know the temperature as well. Or if you're under the vapor dome and you know the temperature, you automatically know the pressure. Because if you're under the vapor dome, these two things are dependent. That means once you know one, you know the other. So here it's telling us that if our pressure is 0.8 bar, water boils at 90. So here, this is our graph, our constant pressure line. This is 0.8 bar. And it's saying that this line here is, what did we say? That's 93.5 degrees Celsius, right? But we're at 220 degrees. So we're looking, where does this 0.8 bar line intersect with this 200 degrees Celsius line, which has to be higher than this, right? So it's going to intersect over here. And again, we have a superheated vapor, right? So we're going to go to tables like we did last time, to these superheated water vapor tables. Now, what we did last time, we looked for 1 bar, right? Because 1 bar was our pressure. But this time, our pressure is 0.8 bar, and the tables in the textbook only give us a value for 0.7 bar and 1 bar. So this is the problem, right? This means we have to interpolate twice, right? So we know that we're somewhere in between these two tables in terms of pressure, and then the temperature we're looking for is 220 degrees. Over here, we're somewhere in between these two values, right? So what I like to do, This is called double interpolation, because now we have to interpolate with pressure and with temperature. So there's a couple different ways we can draw this, right? So here, if you look at this graph, right? So this is, we're trying to find the specific internal energy as a function of the temperature, right? Now, we can, because we're interpolating twice, we need two different interpolation factors, right? We need interpolation factor A, and we need interpolation factor B. And there's two different ways you can go about doing this. So one, you're going to have to interpolate twice with one of these numbers, right? Either A or B, right? Because really we have these solid dots, that's our two tables, right? So in this case, I've interpolated twice with A, right? This open dot and this open dot. But then I had to interpolate with B in between here. Does that make sense? Right? So we can do this first. We can interpolate with A twice, or we could and if we do that, I like to make these tables, right? So this is kind of like tic-tac-toe or something, right? You want to get to the center, right? The center is kind of like where the answer is. But here, if we know, we can either interpolate with temperature first, right? Use A twice, and then interpolate with B to find this value of specific internal energy at whatever pressure is in between our two tables, right? So this is kind of like the table form of what we're doing, right? Or we can go with B twice, which is what's being shown in this graph, right? So here I can draw a straight line between P1 and P2 over here at the high temperature, and between P1 and P2 at the low temperature, and I can interpolate with B first, right? So then it's this same kind of 3x3 matrix, right? But now I'm interpolating with pressure first and then with temperature to find the middle. So I never have to fill in all of the squares here. I only have to get to the middle, right? So what I try to do when I'm doing this is I look for whichever interpolation factor is easier, right? So here what I want for the pressure was 0.8, right? And then what I want for the temperature was 220 degrees, right? So here I'm going to call my interpolation factor A with temperature, right? That's going to be 220 minus 200 divided by 240 minus 200, right? This is going to be 20 divided by 40, or 1/2. Now this one, this is going to be, my interpolation factor B is going to be 0.8 minus 0.7, and we'll divide this by the whole range of 1.0 minus 0.7, right? So this is going to be 0.1 divided by 0.3, right? Or 0.33, right? This is 0.5. Now, when I'm doing interpolation, obviously the number one thing I'm hoping for is that we're right on a row, because then I don't have to do any math, right? I just read the numbers off the table. The second thing I'm hoping for is this, right? This interpolation factor of 0.5, because then I can just take the average between the numbers, right? So in this case, I'm going to want to do this one twice and this one once, right? So I'm going to set up my table here. So instead of using these tables, I'm going to make my own table, right? So here I've got temperatures. Oops. I still don't have the hang exactly of doing this, although my drawing on the board is not really any better. So here, 200 degrees and 240 degrees, and the temperature we're looking for is 220, right? Now, I have a pressure, 0.7, and a pressure of 1.0, and what I'm looking for is P is equal to 0.8. Right? So I know these numbers in the corners, right? Because at 200 degrees and 0.7, this is 2659.1. 2659.1. It's in kilojoules per kilogram. And this 240 is 2719.3. And then over here, my low temperature is 2658.1. And this temperature here is 2718.5. So now, because this is 0.5, my path I'm going to take is I'm going to interpolate here first and here first, because then I can just take the average of these two numbers, and then I'm going to go 1/3 of the way between those two numbers that I get here. Does that make sense? Does anyone have questions about this? So in this case, right, again, I'm going to skip. If you've got a calculator, then you can just do this along with me here. But I'm going to skip showing you the math. I'm going to go right to the numbers here. So this one here is 89.2. And this one is 2688.3. Now, if this was an exam, and you see how these numbers are so close together? It basically doesn't matter. I would, even though this is only supposed to be 1/3 of the way in between, because the difference here is less than 1 kilojoule per kilogram, I would probably on a test say, hey, I'm not actually going to do the interpolation. I'm just going to go halfway, right? Because it's about the same thing, right? I'll do the math here just to show you. But here, these ones, when I'm just taking the averages, I see these numbers are very, very close. So I probably wouldn't, right? And that's actually why they don't give us a table here at 0.08, because it's so close in between here, it doesn't really matter, right? So you could take either one of those values. But let's still set this up, because I want to show you something here, right? So we know that B is equal to 0.33, but it's also going to be equal to U at the pressure we're looking for minus U at P min divided by U at P max minus U at P min. Now, the reason that I want to show you this is because here, when we were interpolating with temperature, our specific internal energy was increasing, right? We were going from 2659 up to 2719. Here, it's actually decreasing a little bit, right? 2689 to 2688. So you got to recognize that here when we're saying U min and U max, it's really U at the minimum pressure and U at the maximum pressure, not the minimum and maximum values of U, right? So here, even though the bigger number is this number, right, I'm going to put that in as U of P min, right? So this is going to be, we're going to isolate this for U of the pressure that we're looking for. This is going to be U at P min plus B times U of P max minus U of P min. Right? But this one is going to be this value, even though this is the bigger value, 2689.2 plus 0.33 times. So this is now going to be a negative number because this is going to be 2688.3 minus 2689.2. So when I do that, I get a value of 2688.9 kilojoules per kilogram. So the thing that we can do if we want to check our interpolations, because if I mixed these things up, I might find that if I do it wrong, I might find that I'm not at a number in between these two values. So just check, like if I messed up the sign here, and I took the bigger number plus something, I would get something above 2689.2, right? But here my number of 2688.9 is between these two values. So like all the time, I don't know if my answer is right, but I do know it has the right units, and I know it's at least in between the two sort of stakes that we have down in the ground. So it does kind of make sense that this could be the right answer. So that's double interpolation, which is sometimes, certainly algebraically, it's the most complicated of these kind of interpolations that we'll do. So does anybody have questions about how we did this? You should have ended up, if you could have taken this alternate path, right, where you interpolated first with pressure and then with temperature, and you should end up with the same number, right, because we're assuming this is all just linear. But if you did, the math would be a little bit more, you'd have to do a little bit more algebra, because it's harder to interpolate a third of the way between these two numbers than just half the way. If your interpolation factor is half, it means you're just taking the average of the two numbers, right? So you just add these two things together, you divide by 2. So the next thing that we're going to look at is what happens if they tell us the pressure, right? So they tell us it's 0.8 bar and a quality of 0.9. So the one thing that we know, anytime they tell us what the quality is, that means we're under the vapor dome. Quality only makes sense if you're here under the vapor dome. Because what quality is, right? Quality is equal to the mass of vapor divided by the total mass in the system. Right? So here I can, I can get rid of this guy here, and we will go through this problem. So here, because we know the pressure, we don't know the temperature, we're going to look for this two-phase table that gives us a nice round pressure in this first column. Now, we're looking between these two values, UF and UG, but I haven't told you what those things mean yet, right? So UF, this would be the specific internal energy if quality is equal to 0. So that means it's only liquid, right? And then UG would be if quality is equal to 1. So that means, right, so if quality is equal to 0, then the mass of vapor is 0, right? So it's 0% vapor, so that means it's all liquid. It's at the right temperature and pressure to boil, but it hasn't started boiling yet. And if the quality is equal to 1, that means that the mass of the vapor is equal to the total mass. So that's only vapor. But it's still this saturated vapor. So basically, if X is equal to 0, you're right on the left-hand side of the vapor dome. And if X is equal to 1, you're right on the right-hand side of the vapor dome. So you're still at the temperature and pressure where boiling is possible, but boiling hasn't happened yet. So what do we do here, right? So now we know that in this case, temperature and pressure are dependent. So I can't fix the state with just temperature and pressure, but that's okay because they gave me the quality. Right? So here, if what I wanted to do, right, so really what I'm saying here is that the U of my mixture at this particular quality is equal to this weighted average mass, right? So this would be like the mass of the liquid divided by the total mass times U of F plus the mass of the vapor divided by the total mass times UG. Does that make sense? We're just taking a weighted average of these two properties. We're saying, okay, if it's 10% liquid and 90% vapor, then it's, the energy would be 90% times the value for the vapor plus 10% times the value for the liquid. Right? But we can simplify this a little bit, right? Because we know that this is equal to X, right? But then we also know something about this, right? Because the total mass is going to be ml plus mv is equal to m total. So ml is equal to m total minus mv, right? Now, if I divided all of these things by the total mass, then what I would get would be that this fraction that I'm looking at is equal to 1 minus x. Right? If it's 25% liquid, then you know it's 75% vapor. Right? So this, I can change this into 1 minus x, right? That's this, times U of F, plus x times UG, right? And now I can collect like terms, and I can say that U of a given quality is equal to UF plus x times UG minus UF. So this is true for U. It's also true for V if I put specific volumes in all of these places. Right? It's going to be true if I put little h's in all of these places. It's also going to be true if I put little s's in all of these places. The only other thing that I want to tell you about this table, and it only matters when we start to talk about H, we have this thing called HFG. We don't have UFG or SFG. This is just going to be HG minus HF. And we're not dealing with H yet, but we will. So if I wrote out if we call this the quality equation, if I wrote this out for H, it would be H of X is equal to HF plus X times HG minus HF. Right? The same is for all of these other things. But this, this line tells us that HFG is equal to HG minus HF. So I can also write this out as HF plus X times HFG. So we don't have to worry about this too much yet. Not till we start looking at open systems. We don't really deal with specific enthalpy too much until then. But I just wanted you to be aware of the nomenclature of what these different variables mean. Right? So that's only there for the H's, so we don't have to worry about it too much. Right? But now we can answer this question. U of the quality here was 0.9 is equal to UF, which is 391. I'm just going to say 6 plus 0.9 times 498.8 minus 391.6. Right? This is all in kilojoules per kilogram. You can see here actually, you see this big energy difference, right? To go from a liquid to a vapor takes a lot of energy, right? That's why my grandmother used to tell me that a watch pot never boils, right? Because to go from liquid water to steam, which is what we're doing when we're boiling water, we have to put a lot of energy into the liquid in order to break those molecules apart so that it's a vapor. Right? So here, we're expecting, because we're 90% vapor, we're expecting to have a number that's much closer to 2498.8 than to 391. Right? So when I put this into my calculator, right, I get 2288.1. Oops. Kilojoules per kilogram. That's going to be U of X, right? So this is our answer here, right? So this is, again, we don't know if it's right, but we got the units right, and we can see it's closer to 2498 than it is to 391. So I feel reasonably good about this one, right? The next one's pretty similar, so I'm going to skip it because I want to show you something with the final answer. The only difference between this next one and the last problem is that it gives us temperature instead of pressure. So because it gives us temperature, we're not going to use this table here, right? Because it gives us a nice round pressure. Instead, we're going to come over here and find this 100-degree line, and we're going to look between these two values of specific enthalpy. And because in this case our quality is 0.25%, we're only going 25% of the range, so we expect it to be closer to this 418. And actually, if this was an exam and it was really quick, right, you could say, oh, the difference between these two numbers is about 2,000. A quarter of that is about 500. So I would expect my number to be somewhere around 925 kilojoules per kilogram here, if I was just doing it quick in my head. Right? Now, sometimes, if it's a multiple choice question, sometimes that's all you need to do because maybe all the other numbers are way far away from that. So sometimes you don't have to go through all the math. Now, this last one, I just want to bring to your attention something, right? So this is, the temperature is 100 degrees. So because we have temperature, we're not going to use this pressure chart. So I can get rid of the pressure chart here. So now we have this 100-degree line, right? So it tells us that it's 100 degrees, but then it doesn't tell us the quality. It's nice when they give us a quality, because when we have quality, we can just move right to finding the specific internal energy. But in this case, they don't, right? They tell us the specific internal, or the specific volume, right? So the first thing that we need to do, right, is figure out if this is a two-phase mixture. Right, so here, if I draw my TV diagram, it looks like this, right? For this given temperature, right, 100 degrees, I know that this value here is going to be VF, and this value here is going to be VG. So this is two-phase if my value here, right, which is 0.9, if it's in between these two values, right? So I want you to take a second and look at these two numbers and tell me if 0.9 is in between these two numbers, right? So here's my first question is, or maybe I would say if VF is less than V is less than VG, then this would be two-phase. But else, if VF is less than, or VF is greater than, V, then this would be a subcooled liquid, right? Because if V is somewhere over here, then this is a subcooled liquid, and then I guess else, if, you could just say else here, I guess, VG is less than V, then this is a superheated vapor, right? So if my V is bigger than VG, then I'm over here, right? And this would be table A3. Under here, because we know the temperature, I think this one is A2, but it could be A3, and this one would be A5, I think. I think that's how it goes. Maybe this was A4. Right? So, what do you think? Do you think that, who thinks it's a subcooled liquid? You don't have to raise your hand or anything, right? Who thinks it's a superheated vapor? And who thinks it's a two-phase mixture? I think when you first look at this, most people are going to say, right, that 0.9 is less than 1.04. Right? So if 0.9 is less than 1.04, it looks like this is going to be this, right? But the table's kind of tricky. To save space, this is not VF. This is VF that's been multiplied by 1,000. Right? So this VF, you have to take these numbers. It's already, this is VF times 1,000. So if you want VF equals whatever the number is over here, right? So if you want to have VF, then you have to take the number and divide it by 1,000. So this is not really 1, it's 1 over 1,000. Right? So in fact, this is a two-phase mixture, even though it didn't necessarily look like it the first time I looked at it. Right? So that's an easy thing that people can mess up if they're not paying attention, is that you have to take this number and divide it by 1,000. Right? The way that I remember this is that the density of water, at least at atmospheric pressure, right, is really always, right, because water is pretty incompressible. The density of water is always about 1,000 kilograms per meter cubed, which means that the specific volume of water always has to be about 1 over 1,000. Right? So now what I have to do is I have to use the quality equation twice. I know that V of my given quality is equal to VF plus X times VG minus VF. Right, now when I look at this equation, the good news is I know VF and I know VG, and the problem told me the specific volume at the given quality, right? So I'm going to take this equation and rearrange it for quality. So this is going to be X is equal to V of X minus VF divided by VG minus VF. Now this is why I teach the interpolation factor the way that I do, because then the interpolation factor, when we talk about A, is really this exact same equation when we're talking about it for quality, right? Because quality is also a linear interpolation between 0% vapor and 100% vapor. But what we actually want to find here is this specific internal energy over here, right? So then we have to use the quality equation again to say that U of X is equal to UF plus X times UG minus UF. Right? Now, at the beginning of the problem, we couldn't have jumped to this because at the beginning of the problem, we didn't know X and we didn't know U of F. So we use this equation here, the quality equation with specific volume, to find X, and then we dump the value into here, and then we use that to find U of X. For this problem, let's see if I can get a value. I got X is equal to 0.53, and quality has no units because it's mass divided by mass. It's just it's not a percentage value because we don't multiply it by 100%. It's a per unit value. Right? And then so here we have this value. So we're about halfway in between these two numbers. Right? And then the value that I got for U of X is 1,462.7 kilojoules per kilogram. Right? So that is how we deal with these problems. Interpolation can be difficult, particularly double interpolation, but I think if you just take your time with it and you think about the process, you'll be okay. The other thing that, particularly on exams, that people can mess up if they're going through it quickly is this thing with the specific volume here, that the specific volume on this two-phase table has been multiplied by 1,000, so it looks like 1, but it's really 1 over 1,000. So that is all that I have for you today. I'm happy to stick around if people have questions. I will also be around in the same room for office hours at 2 o'clock if people have questions about the homework. I extended the homework deadline to today at midnight. If you've already submitted your homework, you're welcome to either delete it or just submit an updated copy, and I'll take the most recent version of the homework that's been submitted. Did anyone have any questions?
I have a question not related to the lecture at all.
Sure.
But do you know the exact dates of when the midterms will be?
I do not. I was going to try to survey the class a little bit because there's so few of us. I think I outlined the weeks where they'll be in but I was going to try to get a poll going. Maybe I should do that sooner rather than later. Just to try to get a day that doesn't have a conflict for anybody, because I know people are doing stuff. So.
Okay. All right, that'd be great.
Yeah. So if you do have a suggestion in the week that we posted, just shoot me an email.
Okay.
And but I'll try to put up a poll or something too.
Okay.
Okay.
All right. Thank you.
Thanks so much.
Also, what where do you post these recordings for the lectures and everything? Because
So if you go to my YouTube channel, I think there's a playlist called Summer 2021. I think I also updated on the weekend because I realized it wasn't on the My Courses page.
Right.
It is on the My Courses page now. I'm just going to try to bring it up here.
Because under live summer lectures on My Courses, I only see 2208 Summer Thermo Live, Summer Thermo L4 Live.
Okay, so let's see if I thought I did this, but didn't do it. I don't know why I can't. So I thought that I put in the description a link to it. You can definitely get to it from the, if you just go to my YouTube page, there's a playlist there. I thought I put a link to the playlist as opposed to the individual exams at the top of the summer thing, but I will go through it once I can get into My Courses. I don't understand why it's not working here.
What's the name of your YouTube channel again?
It's just if you go to any of the videos in My Courses, they're all linked back to my YouTube channel. I think it might just be my name.
I think I found the playlist now.
Okay.
I had to go through your YouTube channel.
Okay, so it looks like there is a link here. I don't see why I can't. It looks like the summer tab is not cooperating here on My Courses. But I'll try to get that sorted out and make it so it's in a little bit more prominent position so it's easier to see.
Okay, thank you, Professor.
Yeah, thanks, Sebastian. And any of that feedback is good for me because I want it to be easy for you guys to use. So thank you.
Okay.
All right.
Thank you.
Thanks, everyone.
All right.